Welcome again to the Rutgers Experimental Math Zoom seminar. Today's speaker is Professor Toufik Mansour from Haifa, who will speak about Ascent sequences avoiding a set of length 3 patterns. As usual, please mute yourself unless you have a question.
Thank you, Doron, for the invitation. Actually, I can suggest another title for the talk, Magically How to Count. So that means what I will present to you about ascent sequences can be applied to other families of combinatorics. For example, inversion sequences, weak ascent sequences, set partitions, K-array words, set partition, set signed inversion, set signed permutations, and so on. So the key, we will see there is some procedure. Actually, the procedure is somehow is basic, but the definition needs generating trees. Let us begin with ascent sequences, and then we will say about that later. In ascent, shortly, ascent index in integer sequence is1 is n is an index j such that is a j less than is a j plus 1. That means like a rise or ascent. In ascent sequence of length n consisting of non-negative integer satisfying the first letter is 0 and then the ith letter is less than number of ascents in a preceding of ai plus 1. The number of ASC A1 to AK is the number of ascent in the sequence A1 to AK. Let me give you example here. For example, this one, look at this. 0 is the first letter. Then I get 0, 1 is 1 ascent. That means the third letter could be 0, either 0 or 1 or 2. So in this case, 0. So if I now look into the first 3 letters, 0, 1, 0, they're 1 ascent. So that means the next letter could be 0 or 1 or 2. In this case, 2. So if I add 2 and I look to the 4 letters, the initial 4 letters, I have 2 ascents. That means the next one could be up to 3, and so on. So this is in ascent sequence. But 0, 1, 0, 4 is not, because if I look to the first 3 letters, I see 0, 1, 0 contains 1 ascent. That means the next letter could be at most 2. But here it's 4. That means it's not ascent sequence. Any question for the definition? Actually, ascent sequences is let us say connected to 2 plus 2 free sets. It's done by Milo, Chrysson, Tux, and Kitaev. Since then, ascent sequences have considered in series of paper where connection to many other combinatorial structure and pattern avoidance actually also considered here, and then asked how many ascent sequences avoiding set of patterns or a fixed pattern. So what I mean by avoiding, so suppose here we have a sequence of integers and a pattern tau that contains the letters from 0 to L of length n. So we say the sequence A contains tau if A has a subsequence that is order isomorphic to tau, which means order isomorphic. That means there is a subsequence of the sequence A AF1 to AFM, such that the two letters AFI and AFJ ordered as TI and TJ. For any relation less or greater or equal. If there is subsequence, that means A contains term. If not, I say A avoids term. And here in the example, the subsequence here 0, 1, 0, 1, 3, 0, 4, 3, 5, 1 has two occurrences of 1, 1, 0, where I can see 1, 1, 0, for example, 1, 1, 1, 0, or 3, 3, 1. So it's the same order. 3 is equal 3, and 3 greater than 1. It's like 1 equal 1, and 1 greater than 0. But it avoids 3, 1, 2, 0 because I cannot find 4 letters as subsequence of this Ascent sequence, such that the greater one is at beginning, then the 3, 1, 2, 0, which has the same order as this one. So I call avoid. All the subsequences, Ascent sequences that avoid a list of patterns, I denote by n the 1 to s, or I just as a list or as set of patterns. If we're talking about avoiding, should be mentioned Wolf equivalence. So what's mean Wolf equivalence in Ascent sequences? I have two sets of patterns. I call B equivalent to Q as a Wolf equivalency if the number of Ascent sequences that avoid the first set, the same number of avoid the second set for any n. Okay, this is the first part of the definition. So I define what meaning Ascent sequences, then I define avoiding, then I define Wolf equivalencies between the sets that I like to restrict or to avoid. Now I will focus on only patterns of length 3. That means I have these possibilities, 13 possibilities from 0, 0 to 2, 1, 0. These are the possibilities of 3 letters that I could avoid. So the question, how many Wolf equivalencies here? So if we avoid one of them, I have 9 Wolf equivalencies. If I avoid 2 of them, I have 35 equivalencies. So usually these 2 results are done by bijections, not a general method that describes how to consider if we have a lot of information or lot of classes that we should look at them. Now I will define AWK to be the number of Wolf equivalences classes of K length 3 patterns. So that means from this set, if I consider K of this 13, and I look to all possibilities, so what is the number of Wolf equivalencies here? So the theorem said AW3 62, 74, 61, 47, up to 1. So Neil, could you ask me if this long concave sequence? No, it's not. And this is my first time that I meet number of Wolf classes that is not long concave. For example, on set partition in permutations, avoiding sets of 4 letters, patterns of 4 letters, it was long concave. but for ascent sequences, see not, because 18 times 35 is greater than 25 squared. Anyway, this is not just is a remark. So the question now, how one can prove such results, especially here we're talking about 2 power 13. That means 8,192 subsets of length 3 patterns we have to consider. So usually we need a computer or something, not a human, to do that, unless he will work on that many years. So the trick is generate trees. So I will define generate trees, then I will say about the main procedure that I will use to achieve such theory. So generate trees, at first let fix be a set of patterns such that each pattern has at least length 2, otherwise it's trivial. It's length 1. Defined AB to be the union of all, that means AB is all the set, all the ascent sequences of any size that avoid B. We construct J3 TD such that the nodes of this tree are exactly the ascent sequences that avoid this set of patterns. Here in this case, actually, I will start as the root 0. And I will say the root 0 stay at level 1. Because why I say the root is stay at level 1? Because 0 is counted as a sequence of length 1. Now we construct the tree TB such that in the nth level of the tree consists of exactly the elements of ascent sequences of length n that avoid the set B. And here we arrange them such that the ascent sequence, the parents of the ascent sequence A1 to AN is A1 to AN-1. That means if I have a ascent sequence and I want to look to its child, I will add at leftmost a letter. Okay, and here is very critical key. Okay, ascent sequences, actually I can add at rightmost a new letter. Weak ascent sequences, I can also add rightmost letter. Inversion sequences are the same. K-array words also the same, but permutation and sign permutation, I should insert the largest letters between the letters of the parents. So that means we have two kinds of insertion. Either I put the largest letter somewhere, or I will add a new letter at leftmost satisfy the conditions. And here it is what the children of this one, it's exactly all the subsequences where I added a new letter such that the new letter is 0, 1 up to the number of ascents in the parents plus 1. And of course, I should check if the new child avoid my restrictions. To make the tree ordered, I should make some order between the children. And here it is. We arrange the nodes from left to right so that if A is equal like this and A prime is equal like this, So are children of the same parents, A1 to A minus 1, then A appears on the left of A prime if the new letter I less than new letter I prime. So that means here I and I prime. Let us take example, and I look to the tree 2011. The first ascent sequences is 0. The next letter, because the number of ascents is 0, so I can add either 0 or 1. And of course, 0, 0 avoids 0, 1, 1, and 0, 1 avoids 0, 1, 1. So I don't care about this level. Now, 0, 0. The number of ascents here, number of ascents is 0. So here I should say, if the number of ascents is 0, I should add either 0 or 1, and both avoid 0, 1, 1. If it's 0, 1, there one ascent here, so I could add 0 or 1 or 2. But if I add 1, I get 0, 1, 1, which contains 0, 1, 1, then this is not possible. Then I make level 1, level 2, 3, and 4, and I make the tree. What is the problem in this tree? There are many different nodes. So could we consider the same tree in different sense, such that I don't see many different nodes? Let us say less different nodes. And here it is what we are going to do. I define TBA, the subtree of TB of the ascent sequence A as the root and its all children or descents below it in the tree. For example, this is the tree T01100. And this is another tree, but the root is 0 and all its children. For any two ascent sequences A prime in the tree, we say the subtree this and this one are isomorphic, and we write in this way: if these subtrees are isomorphic in the sense of a plane ordered tree. Because why I used order? Actually, ordering is not important. Because, for example, I will give you an example here in way this tree and this tree 1, 2, 3, 1, 3, 2, and here 0, 0. For example, these two trees is not the same tree, is not isomorphic as ordinary tree. But because I'm interested in counting how many children in level 1 is 3 and here is 3, so the ordering is not important. But the ordering, usually I use it when I want to prove something about the children. So for any two nodes, A1 in the tree, we say that A is equivalent to A prime, denoted by this, if the subtrees are isomorphic. Now, this is the key: define VB to be the set of all equivalency classes in the tree up to this isomorphic relation, up to this relation. So now here it is the critical one. We will represent each equivalence class B by the level of the unique node V, which appears on the tree as the leftmost node at the lowest level among all other nodes in the same equivalence class. So that means we have equivalence classes. So I choose the first one that appeared and put it instead other, all other, or anyone that equivalent to it, up to my relation. And here is the example that we started 0, 1, 1. So it's 0, 0, 0, 0, 1. It's different because let us say y 0, 1. It's, you see, this is the tree that we considered before. Now I want to consider its equivalence classes. So 0 is 0. It's new one. Now I found 0, 0. I look to 0, 0. Any ascent sequences started by 0, 0 that avoid 0, 1, 1, I can map it to ascent sequences that start by 0 only, by removing one of the zeros, to avoid if 0, 1, 1. That means if and only if. Because that 0, 0, 0 and 0 are equivalent. So I can replace 0, 0 by only the new equivalence class that I choose 0 because 0 appeared before 0, 0. And so on. 0, 1, the same. If I have 0, 1, let us suppose we have ascent sequences start by 0, 1. Because we avoid 0, 1, 1, there are no more 1. So what is the next letter? Should be 0 or 2. 1, it's not possible. If it's, I put 1 here, I create 0, 1, 1. So it's not possible. So this sequence, I can map it to another sequence. It's by removing the 0 here, I remove, and each letter I decrease by 1, but not the 0. So it will be 0, the 1 mapped to the 0, all the letters here, 0 mapped to 0, and an x mapped to x minus 1. So A avoids 0, 1, 1, and only if A prime avoids 0, 1, 1. So that means 0, 1, it's equivalent to 0. So I put 0. So I get new tree. Here it is. Symbol 0 have 2 children, 0, 0. So, and for counting, of course, I can to count how many children have the 0. It's easy to see in this tree, in the tree, the new tree, instead to see that in the old tree. So this is the trick actually. So let me give you example now more complicated. Let us say I have three patterns 0, 0, 0, 0, 0, 1, 0, 2, 1, and I want to build the generic tree. So here are the rules. I will explain how I guessed the rules. So at first I guessed some rules, and here it is, and I know what is AM and BM and CM. Now suppose I want to prove this rule. It's easy. CM, I know any children of CM, for example, I'm going to prove this one. Any children of CM, what I doing? Let us write CM in full notation. So 0, 1, 2, M, M. I want another child. So the children of this ascent sequence are 0, 1, M, M. I want to add a letter J. But the letter J, because we avoid 0, 0, 1, and 0, 0, 0, and 0, 2, 1, I should be careful. So because 0, M, J should be the J or 0 or greater or m or greater than n. So I have conditions. Using this condition, easy to prove the rule and another rule, and like that I get the tree. So what is the procedure? What is the procedure to get the tree? First, I have set of patterns. I put some number t positive, how many levels I would like to check the tree. For example, d equal 8 in my, to prove the theorem for either 3 patterns or 4 or 13, it's enough d equal 8. We find the first d levels of this generic tree by computer. Usually I programmed that, and then here it is, I failed to program giving a set of rules. Let us say set of rules means rules of the first d levels of a tree. Can we construct automatically from this set of rules a set of rules but indexed by some indices? I will explain later what I mean. So we guess all the succession rule of TB. For example, let us back to our tree. Here it is. So here, this tree, 0 going to 0, 0, 0, 1. 0, 0 give you 3 zeros, 0, 0, 1. 3 zeros give you 4 zeros, 3, 0, 1. And more there, 0, 1, 0, 0, 1, and 0, 1, 0. I should write it. So the program is actually giving set of patterns. Here it's I have 4 levels, d equal 4. So the computer gives you all the rules for the first 4 levels. Then after you look at this, you say, now I want to make this tree. So after the relation, I get this tree. So here is the tree is finite. 0 gives 0, 0. So that means I have only one rule, so the number of rules is fine. But for this tree, for example, here I have many rules. So that means infinite rules, that means the tree is not finite. So I want to consider, remember, these rules, I get them for m at most d. Then I prove that for any n. So back to general procedure. So at beginning, I built the 3TB for first d levels. Then I built the succession rules from them. I guessed them, actually. Based on the step, and this is step 3, I try to prove this succession rules. If we fail, there are 2 possibilities. Either I need more information on the tree, so that means to increase d, or I say, or I already, the succession rules already found. So that means I done. After I done the second step in the general procedure. So the second step is the following. I would like to find the generic tree, the generated function fbx, which is the number of Ascent sequences that avoid the set, all the patterns in the set B. And here to do that, to find explicit formula for FB, or to study this generic function, I define the generic function AE So for given a rule E, parents E, and has children V1 to Vs, I define a E as x plus x sum over all the generic function of a Vs. So that means if the number of the nodes at the subtree with root E is the number that the children or number of the nodes in each subtree V1, Vs shifted by 1 because the level is shifted by 1. And AW is the number of the nodes in the level N in the subtree TBW. So this is the generic function. So now let us, okay, this is the general procedure. So the general procedure is divided to 3 steps actually. First step to build the tree, then to build the tree with equivalence classes, then to guess the rules. This is the first step. Second step is to convert the succession rules to generic function. The third step is to solve the system of the equation that you got. So to solve the system of the equation, it's also need somehow magic, I don't know, but usually can be done by induction, can be done by kernel method, or any other methods, combinatorial method that lucky to find the solution. Most of the time, we're not lucky. So, and here are the troubles. Let us say about 3 patterns of length 3. A candidate class is a maximal subset C of L. L is the set of all patterns of length 3, such that the number of ascent sequences avoiding B and ascent sequences avoiding B prime are the same up to 11. Why 11? Because when I run the programming about avoiding a set of patterns, it was easy to 11 such that I will not wait a lot of time. Actually, it was enough for me to see to guess what are the Wolf classes here. A candidate class is called trivial if it contains only one trouble. That means one sets that the numbers from 1 to 11 are different from all others. So that means the Wolf class is exactly the trivial class. If it's otherwise, it's not trivial. That means in my candidate class, there is 2 sets have the same numbers up to from N1 to N. So I need either to find, for example, the generic function here and the generic function here and prove they are equal, or I need to prove the trees are equal, the generic trees are equal, or I should disprove that to find the numbers of ascent sequences avoiding B and ascent sequences avoiding B prime are not equal. Clearly, any Wolf equivalence class is contained in a candidate class. So it's contained in, but not the other direction. There are 35 trivial candidate class and 27 non-trivial candidate class of troubles. And to prove there are 62 Wolf classes, we need to show that the 27 non-trivial candidate classes of troubles are indeed 27 Wolf classes, because 35, 27 plus 62, it's easy. So that means it remains to me to show this non-trivial candidates are exactly with equivalences. Okay, here it is. So my programming, what doing? Scanning all the possibilities of troubles and for each give me the rules, of course, in not such table. So I said, when I run the program, for example, in the first case here, this is the output of program. But in the case here, because the table is contained, the generate tree contains infinite number of labels, so I guessed the rules and then I prove the rules. So because here I used one index, and what is surprising, most the cases are with one index, but there are many cases also with needed more than two indices or even three indices to describe the succession rules. So anyway, this table contains the number of the class, the sets of patterns in the candidate class, the succession rules for each, and the generic function. And then if we look, we will see all the calculations. It's huge, and somewhere I put C. That means some people did that before. And I will not, of course, say each one, but sometimes I use C section. That means my program failed. So I didn't successful to guess the rules. So in this case, I need another combinatorial trick to prove they are the same. So usually, if I fail, I use bijections. So between one class to another.
So officially, it's only a conjecture. It's not approved yet, right?
No, all is proved.
Ah.
In this case, all is proved.
Ah, that's nice.
But failed means the program failed. I didn't successful to use the program to guess the rules.
Ah, thank you.
And here, as you see also this. This means these two cases are done by someone. So again, as you see also here, so not a small number of cases to need to cover. So actually, if I look how many cases, it was 2.13 subsets. How many programs successful from this? More than 25%. We succeed. But still 5% to do. So this is not covered by table 1. So for example, in one class, this one and this one is just simple number, just simple counting, 2 power n minus 1. Should be not hard to prove this. Actually, combinatorially, it's easy, and it's written here. I will not say more than this, but this, if the program fails, this doesn't mean the generic function is complicated. Maybe it's rational. And most of the time, if it's rational, it's easy to prove by projection or by direct counting, not generic trees. But if it's not rational, the proof of counting, it's more complicated than I used projections. And how we proved in this case, let n be this number. Clearly, A1 equal 1 because there are one ascent sequence which is 0, and A2 is 2 because there are two ascent sequences is 0, 0, 0, 1. So I will assume at least 3. So any ascent sequences avoid this 3 patterns, I can write in this form: 0 or ascent sequences plus 1 for each letter, or 0 and their ascent sequences between plus 1, or 0, 0 and ascent sequences plus 1. So now with the counting, it's easy, and you get 2 power n minus 1. The other case, here it is, but here the program, actually, the Baxter and Badwell showing that the generic trees for this ascent sequences are here, is given by this generic tree. And if I do the translation from the sectional rules to system of equations, I donate by a k, the generic function, x for the root, k minus 1, here it is k minus 1, because it's k minus 1 times of the node 1. So x, because I move to another level, a1, because here 1. And k plus 1, it's exactly x times ak plus 1. And also a1 in succession rules of 1 give 2, it's a1 equal x plus xa2. Okay. Define the generic function of this, k vk minus 2 sum over k at least 2. I get the functional equation, this one, from only this. So this is the generic function, can be solved by kernel method. So what means kernel method? That means if I take v equal x here, so if I put x here instead v, x over x is 1, so this will be cancelled by this. Only I should care that my substitution give me power series that with the positive coefficients, and there's nothing that I say not standard in my counting. Anyway, so in this case, indeed, if I take v equal x, I get this generic function, this relation, a2 equal this one. So I get the relation between a1 and a2. But I have another relation between a1 and 2, which is this one. So I have two relations. Solving them, I get a2 equal x over 1 minus tx, and a1, of course, if I put here x plus x times x over 1 minus tx, I get what it's needed. So here we was lucky that the generic trees of this, the second case of the second candidate, is known. Sometimes not. So what if it's not? So I said If it's not, then I will use bijections between the corresponding sets. Okay, class 28. Also, I have a problem. So it was this another story, another example actually. So I have three sets in this class. I want to show bijection between them, or that the number of Ascent sequences avoid the first one, it's the same, avoid the second one, and the same, avoid the third one. So since an Ascent sequence begins with 0, if it contains either 201 or T10, then it contains 021. Well, let me explain this by, here it is Ascent sequence. This Ascent sequence start by 0, and here 201. 201. Because here 0, 0, 2, 1. So if it contains 201, that means it's contained 201. Because that, you see, this, it's the same to avoid this one. And this, it's the same to avoid this one. So to avoid these 3 patterns, it's the same to avoid these 2 patterns. What about 100? Also, let us say, if an Ascent sequence contains 100, then it also contains 30 and 021. Either this or this. Let us try to explain this. Here it is. And let us assume we have 1, 0, 0. So there are 2 possibilities. Or this zeros, in this case 0, 0, 0, 3 zeros, or this is bigger than 0. That means at least 1. So in this case, if this is at least 1, this means at least 2. So that means 0, 2, 1. And this 0, 2, 1. The opposite, of course, it's also true. So that means this is like to avoid 0, 0, 0, 0, 2, 1. Because this equal this to equal this, that means all these 3 classes, 3 sets belongs to the same Wolf equivalence class. Okay, there are more cases actually. There are more cases to show. Most of them are different. And here, for example, I used, you see, 2 indices to describe my rules. In this case, I define I prove the trees are and the children of them, and then I studied the other tree and I found another rules, and I map the rules to the rules, and then I solved the system by translating to general functions. I will not ask, but describe this kind of functional equation that I deal with it. And this is actually, as you see, we have extra 2 variables and division. And
so you also have Catalan numbers. Wow.
Yeah,
that's nice.
Yeah, but remember how I solve this. There are 2. Usually people solve the functional equation by trying to make substitution to cancel the kernel. In my case, sometimes easy to guess the solution. And if I guess the solution, it's easy to check. And this sometimes helped me to solve. And here it is. We assume that x00 is this. That means I need to prove that. If I assume this and I solve the equation under this assumption, I get solution satisfy AX00 equal Catalan minus 1. And this is actually like that. I assume this, then I use substitution, then I guess AX1V, then I found AXVU, very complicated, then I show it that my solution, general solution, satisfy the equation and satisfy the assumption. And here is what we found. This is given by Catalan number.
A beautiful result. Do you have a bisection?
Actually, for this case, I don't remember 100%.
Okay.
But what I remember, there it was two candidates in this class. One of them we have bijection, and another one we have enumeration on.
Anyway, beautiful.
Okay, for further results, as I said, I have all this.
Thank you very much for a great experimental math talk. Very, very, so some of it is really guessing, but then it's very rigorous at the end. So it's really perfect. Any question for Toufik?
Yes. I may ask something.
Yeah.
So it is well known that these ascent sequences are in bijection with 2, 3, 1 avoiders, right?
Yes.
Yeah. So is it true that some of these classes you found have corresponding classes of permutations avoiding other paths?
There is. Of course, for example, one of such, I don't know if it's bijectively, but I saw that the numbers are the same. So you see, when, for example, when I get the number 2 minus 1, of course, when you take permutation avoiding this 2, you get also t power n minus 1, right?
Yeah.
So that means it should be bijection between ascent sequences here and the permutation here. But you see, because this is very nice number, I didn't try. Because my program already did that directly, easily. I found the general function, so I didn't find the bijection. When I found the bijection, only for the difficult, the hard cases, let us say hard cases, that means the procedure failed to deal with them.
Sure, but here, are these patterns avoiding those ascent sequences corresponding somehow to 1, 2, 3, 1, 3, 2, or?
You need the bijection. I don't know. I cannot say these ascent sequences are easily mapped to this permutation. I cannot say such a thing. And also I cannot say it's hard. I don't know. Actually, I don't care for this case. For example, you see, in one cases, I showed you the first, now this one, you see? This one. So in this case, I get the same number, right? So that means the sequences avoiding these 3 patterns are the same as number of permutation. So is there bijection? I don't know. I didn't try. But seem to me it's easy in this case because the characterization of these sequences are similar to characterization of the permutation.
Oh, I see. Okay, thanks.
More questions to Toufik? So I have a quick question. So for each of the classes, you have exact enumeration. You have generating functions, right? or some of them you don't?
Yeah, for the trivial classes, that means the wealthy classes that contains only one set, I did not try to find all of them.
Ah,
Most of them, I know what is the GA function, but because the length of the paper, we keep this GA function out of the paper or out of the research.
thank you.
But let us say the trivial, my feeling, if you're asking my feeling, I say the trivial classes harder than the non-trivial classes.
That's funny. Paradox. Okay. Well, it's almost 1 a.m. next day to
Yeah.
Toufik. So we wish him good night. Thank you, Toufik, for a great talk.
Thanks.
And please send me the slides tomorrow. Go to sleep. Good.
Sure.
Thanks for coming and see you next week. Thank you. Bye-bye.
Bye-bye.
Sarah, please end this.
Bye bye.
Thank you. Bye-bye. Thank you.
Thank you.